Hello, my name is Shim, and this is my course project for CAP 6415 Computer Vision course. My project is titled Energy Cost Prediction on Various Terrains for Ground Robots Using Multimodal Sensing. The aim of this project is to utilize and train a neural network model to predict the amount of energy required by an unmanned ground vehicle or UGV to navigate through various types of terrains. For instance, the UGV I worked with is capable of traversing through terrains such as grass, concrete, rocky surfaces, and other types of terrains where the energy cost that the UGV will require will likely be different depending on the terrain it's traveling through. Being able to accurately predict the energy cost a UGV requires depending on the surface it navigates through can be useful for preventing incomplete tasks or mission failures being performed by the UGV. To train a neural network, we implemented multimodal sensing by gathering information about the UGV's terrain through a camera to collect images on the terrain, and also from various sensors on the ground vehicle, including a GPS system and inertial measurement unit data. For the purposes of this computer vision course project, I will mainly be focusing my discussions on the camera implementation and the neural network training and testing, as these topics are most relevant to the topics studied within this course. The neural network models used in this project are the ResNet 18 pre-trained model, which is a convolutional neural network model, which is mainly used to extract numerical features from the captured camera images. Additionally, a multi-layer perception model is trained on the numerical image features and on the numerical data obtained from the other sensors located on the UGV. With the trained model, we aim to predict the energy cost measured in joules per meter of the UGV when traversing through a terrain. This is my GitHub repository where you can find a summary or abstract about this project as well as information about the sources I used. You will also see two Google Drive links to the image datasets that will be used to run the codes for training and testing the model. The image datasets cannot be uploaded to this GitHub repository due to GitHub file size restrictions, so instead, you can download the image data from these links. In this energy consumption prediction files folder, you can find more folders containing the codes utilized for this project, which I will run later in this video. You can also find the training and testing data from the UGV's sensors in this data folder. And as I stated earlier, the image data is not stored within this GitHub repository due to size limitations, so if you download the training and testing image datasets from the provided Google Drive links, you will have to copy the training image dataset into the training dataset folder here, and then the test image dataset will need to be copied in the testing dataset folder here. Images of the results, visualizations, and a video demonstration can all be found in the results folder here. So now I'm going to run my first code, which is used for loading the data collected from the camera attached to the ground vehicle, as well as loading the telemetry and GPS data collected from the vehicle during data collection. Since the collected data is saved in 3 different CSV files, the script merges and aligns the data based on time so that each collected data point corresponds with one another. Since our goal is to predict the energy consumption of the ground vehicle based on the terrain it's navigating through, we obtain ground truth values using the power and speed values, which are obtained by the collected telemetry data of the vehicle. This code uses a pre-trained convolutional neural network called ResNet 18 that converts the image data of the terrain into a numeric feature vector. Additionally, multi-layer perception is utilized by combining the image features, the numerical data collected by the other sensors on the ground vehicle, such as speed, distance traveled, elevation, etc., and the ground truth energy per meter values that are obtained by dividing power over speed, in which these values and information is used to train the model so that it can learn how to predict the energy, which is measured in energy per meter. Additionally, here are some of the required dependencies that need to be installed to run this code, as well as additional information. The code finished running, and since I don't have a GPU on this device, this code took about 1 hour and 18 minutes long to fully run. Now that we have results, we can analyze these metrics. When comparing the first epoch to the last epoch, we can see that overall, the values of the metrics seem to improve. For instance, the mean squared error goes down quite a bit, indicating how the model's predictions become much closer to the actual energy cost values. The mean absolute error also decreases, where in the last epoch, we can see that our model is about 41.12 joules per meter off from the actual energy cost value. When analyzing the mean absolute relative error values, we can see how in the first epoch our model had an average error of approximately 62%, but in the final epoch the average error was approximately 15%, showing how the model was able to learn about the terrain patterns. Lastly, the R-squared values go from negative 6.1606 in the first epoch to 0.4810 in the last epoch. Initially, our model had a negative R-squared value since it barely was able to learn. However, in the last epoch, we can see that our model improved and was able to explain about 48% of the variability in energy consumption. When taking a look at the performance of the trained model on the test set, we can see that our model's predictions are off by about 53.08 joules per meter when analyzing the root mean squared error value. Additionally, the mean absolute error value is 41.8815, which represents how our model's predicted energy cost values are on average off by 41.8815 joules per meter from the actual energy cost values. Also, the energy cost predictions from our trained model are not that off, considering the mean absolute relative error indicates that the predictions are about 15.87% off from the true energy values, and since the R-squared value shows that the model explains approximately 45% of the variation in energy consumption for the test set. Overall, considering that the collected data may contain some noise, our model seemed to learn how to predict the energy consumption of our ground vehicle fairly well, as we can see when analyzing the various metrics values we obtained. Also, considering that the validation and test metric values are close, then overfitting is not really present in this model. Here is another script used in this project where this script is used to evaluate our trained model by testing it on a separate test dataset that was collected. In this script, the trained model is loaded and evaluated on the test dataset by outputting various metrics in a scatter plot in order to analyze the performance of the trained model. Here are the dependencies needed for running this code along with additional information. The code finished running and it took about 1 minute and 40 seconds to run on my device. We now have our output and we can analyze the performance of our trained model on the test dataset. When analyzing the metrics, we can see that the root mean square error indicates that our model's energy cost predictions are off by about 73.94 joules per meter as compared to the actual energy cost values. In addition, the mean absolute error shows that on average, there is a difference of about 58.63 joules per meter from the predicted energy values and the true energy cost values. The metric that shows how our trained model does not have good generalization is the mean absolute relative error metric. Since the value for the mean absolute relative error is about 27%, we can conclude that our model's predictions are moderately accurate. Previously, when we tested our trained model on the test set that was obtained by splitting the training dataset, we obtained a mean absolute relative error of approximately 16%. Since we now get a mean absolute relative error of 27% when testing the model on an actual test dataset, we can conclude that we may have some generalization issues. Lastly, the R-squared value is negative 0.5956, where we can see that the model is not capturing the variation in the dataset. The negative R-squared value means that our model's predicted values are not good, where the model's performance is actually worse than if a model were to just use the average energy cost value for every predicted output value. Some reasons as to why this may have occurred is that our test image data is a bit different from our training image data, and this is because we ended up moving the position of the camera after collecting the training image data, resulting in the test image data to capture the terrain from a different angle. Additionally, our training dataset was small, which may have caused the model to not be capable enough to work well with the given test dataset. Additionally, a scatter plot showing the predicted versus true energy per meter values was produced. From this plot, we can see that most of the energy predictions are around 200 to 300 joules per meter, showing how the model often predicted an energy value that was in the middle. This plot also shows how the model struggled to predict energy cost values that were either very high or very low, since we don't see many values near the upper right of the plot, around 350 to 500, and barely any values in the lower left of the plot, around 100 to 150. From this plot, We can conclude that the model's energy predictions rarely changed despite the true energy cost values changing a lot. This script also outputted a CSV file showing the model's predicted energy cost values in joules per meter and the true energy cost values in joules per meter. As you can see, the model was able to predict some energy cost values well, but also predicted some energy cost values poorly. As we saw in the previous scatter plot, the majority of the model's predictions were within the 200 to 300 range, which we would likely notice if we went through the rest of the predicted values in this file. Overall, the results shown from testing our trained model on the test dataset indicate the presence of a domain shift where our test dataset is different from the training dataset. When taking a look at our training images versus our testing images, we can clearly see that the angle at which the images were taken was completely different. Although our model did learn real patterns as seen when we tested our model on the first test set, which resulted in an R-squared value of 0.45, our model couldn't generalize well enough to the actual test dataset. In the future, I hope to improve the trained model's performance in order to get more accurate energy cost predictions. Currently, the metric values such as the mean absolute relative error was about 27% when testing the model on the test dataset. My plan is to reduce this value as much as possible to have a much more accurate and reliable model. One approach I plan to take in the future is to recollect training data using the updated camera position that was used when collecting the testing dataset. By having the camera position stay at the same position for both training and testing datasets, the model should perform better. Additionally, I plan to collect more image data to train the model where this should help to improve the model's generalizability. Another way the model's generalizability can be improved is through training the model on more types of terrains. This will also make the model more capable since it would be able to predict energy consumption on surfaces such as rocky, concrete, dirt, or other surfaces than only grassy terrains, since the current project only consisted of training and testing the model on grassy terrains. This is my project on using multimodal sensing to train a neural network model for predicting the energy cost of a UGV when navigating through various terrains. Thank you.